Okay, now in this question it's just a bond enthalpy question, so just need to make sure we know this formula, which is reactants, or the sum of the reactants minus the sum of the products for the enthalpy of bond formation. Now it's important obviously to be able to write the balanced equation correctly, and with this, and if we look at the bond enthalpies, we're then just adding up the reactants and subtracting the products. Now in this case, the only thing that's going to be really tricky in many respects is going to be the actual structure of silicon dioxide, the giant covalent lattice, and that's because it's tempting just to write it as two single bonds to an oxygen, but if you recall, it's a little bit like any other giant covalent network, or not any other, but more like perhaps diamond. It's bonded to actually four other structures, or in this case each silicon is bonded to four other atoms. So even though it's written SiO2, that's the empirical formula for it, but the actual bonds, there's going to be four bonds that either are going to actually end up being produced when this is made. So we just have to make sure, and that's where you're most likely to go wrong in this question. It's going to be four bonds that end up getting formed. So if we add up all of those, it's 996 for the oxygens, it's 1292 for the silicon hydrogen, and 1864 for the silicon oxygen, and 4 OH bonds. If we add those up and subtract them, we'll end up with minus 1428 kilojoules per mole. Okay, so just one little trick to that one there. Okay, so if we look at the methane combustion one, that's a little bit more straightforward. The structure's more familiar to you. If you write out the reaction, often it's also a good idea to write out the structural formula to make sure you don't miss a bond and you don't mistake a single bond for a double bond or something like that. But if we add those up, we've got the reactants 1652 plus 996, subtract 1608 and 1852. We'll end up with overall minus 812 kilojoules per mole. And as these are both negative values, that means they're likely to be both favourable reactions. Now, one thing we should comment on in here is the fact that if we look at this, it says that the silane ignites spontaneously, and if anything reacts spontaneously, it tells us something about the activation energy, and obviously it tells us that this has to be pretty low in order to get the reaction going. So it's got must have significantly lower activation energy than methane, so it takes less, and that's that one.